Hey everyone, good afternoon. This is Venkatesh. I welcome everyone here on behalf of Skilling. I'll be hosting the session today. For those of you engaging with Skilling for the first time, we are an engineering upskilling platform focused on advanced technologies across mechanical, electrical, electronics, computer science, etc. This webinar is brought to you by our enterprise business, which focuses on employee training and upskilling across industries, including automotive, consumer electronics, ITES firms across various verticals. Today's webinar is on simulation-aware design. This is the 24th edition of our webinar for corporate professionals. Some pointers before we start the session. Please post your questions on the chat window. Mr. Subbu will take it up during this session. There will be a feedback form which will float towards the end of the session. Kindly spare a minute and fill it up. Also, for people who need recording of the session, kindly request the same in the feedback form. About today's instructor, Mr. Subbu. He's the category head for mechanical engineering at Skilling with over 15 years of experience across various design and development roles in top automotive OEMs such as R&T BCI, MBRDI, and Scania. He's skilled in sheet metal, castings, engineering plastics, GD&T, product design, CAD, and simulation of engineering. With deep insights into both design intent and manufacturability, Subbu brings the practical and industry-focused lens to CAD CAE integration. Over to you, Mr. Subbu. We look forward to hearing from you.
Thank you, Venkatesh. Was nice introduction. Didn't expect. And hello all. Thank you for taking time and joining the session. I hope I don't waste either of our times. Taking a break from your regular work activity and listening to such a context itself is adding a lot of value to me and adding a lot of responsibility to me. I hope I satisfy the requirement. Throughout the session, at any point of time, you can drop in your questions on the chat box. I try to answer from the little knowledge I've gathered during these 15, 16 years of experience. Yes, so I think we can directly jump into today's presentation. I'll start presenting the screen and we'll see how far we go forward, right? So today, this is going to be an interesting topic is what I feel. Since I'm sharing the screen, I'm not able to see. So Venkatesh, it would be helpful if you find, if you can let me know if there are 4 or 5 questions accumulated so I can pause the presentation and then move forward, right?
Noted, Mr. Yeah.
Yes. So, okay, I'm basically not a presentation-based person, but today I made sure that I make a neat presentation so it is valuable for everybody. And the agenda today is to first let us understand what is the workforce, how is design and simulation playing a key role on the automotive industry. I'm talking about the number of people involved in it. And second, we'll understand what simulation-based design is, right? And what should a designer have in mind when a designer designs a part? It could be a plastic designer or a metal designer. Here, a lot of thicknesses plays a role, a lot of fillets plays a role, right? What should a person have in mind? When we say like these should be your perspectives, these should be your inputs, you will have to also understand why is it that, right? So we are talking about load path and their analysis. So this could be the load path if this is the type of product. So this is how your progress would be. So that is the understanding. And I would also want to show some common mistakes what as a design engineer we do in our daily lives by some smaller examples and how can we avoid that. And we will also see what is the reason for us to avoid that, right? Because not all problems are actually problems. Sometimes there is no mistake at all. It is all about how do we take it forward, right? So that is the entire idea. And I also have made a small career roadmap for this hybrid kind of engineer. So I strongly believe that if you have only one skill, it would be difficult for you to survive in the industry in next 5 years. So one should wear multiple hats in the industry to understand or to shine themselves or grow themselves in their career, and that is the present need of the heart, right? So we'll start with the first point. I'm just taking an example, sir. I like telling stories, so I would take it like in a story way, right? Let us consider that there are 3 OEMs in the country. For example, Mahindra, Suzuki, Tata, right? The basic case study or basic understanding is for every engineer in an OEM, there are 4 engineers working outside an OEM. If Mahindra is recruiting one engineer, there are 4 engineers who is going to work for this engineer. That could be on any capacity. It can either be on design or supplier quality or production, whatever, right? So for one, there are 4 engineers working. This is a basic understanding what we can have. Consider this is not even a lame example. This is the reality what is happening in the industry, right? For a vehicle to be built, there are 1,000 engineers needed. So, for example, if there are 3 OEMs and each OEM makes 3 cars here, we are already talking about 9,000 engineers needed in the OEM only, right? If for this 9,000 engineers, if we are talking about around 4 engineers, we are talking about a demand of almost 45,000 engineers in total involved every year for launching 3 cars per 3 cars per, 9 cars a year. But the reality is globally, we are not talking about 45,000 engineers, or globally, we are not talking about only 9 models getting launched in a year. We are talking about severe number of models. If you take about Mercedes-Benz, they spend around 5 years developing product. If you talk about Tesla, it would be surprising for you to know they spend only 3 years to develop a model. Meaning, Mercedes-Benz, the number of workforce could be lesser. Tesla, the workforce needed is more because they wanted to develop in 3 years' time and launch the product. And same way goes to Suzuki also. We can also compare with the Nissan's car. If you see Nissan Quid, it was launched, Renault Quid, sorry. It was done both by Renault and Nissan engineers. If you see Renault Quid, the pre-development phase was only 2 years. So we are talking about on an average of 45,000 engineers involved every year. Out of this 45,000, 50% goes to production. So let us consider 22,500. The remaining 50% comes to R&D, which is the key area what we are talking about. Key area. This 22,500, if you see, almost 30 to 40,000, 30 to 40% of these people would be experienced people. When I say working professional, I'm talking about high experienced people. For me, freshers is from 0 to 3.5 years. We are still fresher because up to 3.5 years, I myself have designed only a smaller bracket. If you know Nissan Micra Active, you have this assist grip inside the car. The person who is sitting behind used to hold a grip inside, right? Behind this grip, there used to be a metal bracket, which is joining the grip and the body together. That was my first design. And I did this design when I was 3 years experienced. So up to 0, from 0 to 3.5 years experience, I would still say we are all freshers. From 4 to 10 years experience, I would say we are all mid-career stars. 10 plus years, we are all experts or whatever, right? So out of these 22,500 engineers, around 30 to 40, 35% or 40%, we are already talking about working professionals. And this 50 to 60% of freshers play a key role developing the product, play a key role bringing in competency or bringing in new things. So that number comes to around 15,000 per year, right? So of course, when you consider attritions, people going out and coming in, so every year's demand is not going to be like this. Every year we are talking about at least 15 to 16,000 in one country. Globally, if we see, the demand is really focused, and this 15,000 is spread across 2 major domains. One is design and one is simulation. Right? Moving forward, this design and this simulation will merge together and everybody will become development engineer because people wanted this hybrid skills, right? So one team will focus on developing the design. Today, one team is focusing on developing the design, and today one team is focusing on validating the design, whatever is developed. Later, in 5 years, 6 years down the line, what we are thinking about is this person who is developing this design should already have certain set of skills that he or she knows if this design will work or not. There should not be a lot of time spent during this validation phase. That is the thought process, right? Initially, we used to design, build a physical product, do simulations physically, and then understand. The advancement was these simulation tools. These simulation tools, we used to do certain activities in it, and then we started doing this, where we reduced a lot of cost in physically building the product, and this time, cost, money, energy we saved there. Now the situation is the designer himself, if he or she knows the concept of the simulations, that is going to add a lot of value, and there we will again reduce a lot of time, money, energy, resources, right? That is the thought process here. When we are talking about all these things, we will have to understand a major difference between designer and design engineer. Every time when a person, if somebody is asking you, it is very easy to tell that I am a design engineer. But we will have to look into what role a person does and then say what is design engineering and what is designing, right? For me, designer is a person who converts 2D drawing to a 3D model. Design engineer is a person who knows the values which goes behind these 2D drawings. Meaning, if a 2D drawing of, say, for this mobile phone, if it says, okay, 30 millimeters, 10 millimeters, why is it 30 millimeter? Why is it 10 millimeter? A person who understands the reason for this is called as a design engineer. A person who converts the 2D drawing to 3D model is only a designer. So for a person to understand the reason behind, he or she should know the functionality of the part, manufacturability of the part, and assembly of the part. Meaning, you being a design engineer sitting in front of computer modeling the components is not sufficient. You should know how are these components getting produced, because manufacturability aspect is a very important aspect for you to include on your design aspects. Similarly, today we will focus on how does simulation based design work on, right? And on that note, inside the R&D field, again, simulations there are multiple type of simulations. Majorly used simulations inside the R&D team or the automotive industry is CAE, CFD, and MBD. What is the primary difference between CAE, CFD, and MBD? CAE is any simulation you do on the component. This is a component. If I do a simulation on the component, it is a CAE simulation. If I do a simulation around the component, it is CFD simulation. Now an example. Frontal crash analysis is a CAE simulation. Aerodynamic analysis is a CFD simulation. Multi-body dynamics is steering angle, suspension movement, etc., etc. So majorly we are talking about CAE or CFD type of simulations, which is experienced, which the automotive industry experiences. Whatever could be the simulation model, there are three important stages one will follow. This is just for you all. I believe that most of you here who has joined this forum is design engineers. So just as an introduction, I would say. Majorly, there are three steps involved, right? One would be pre-processing, solving, and post-processing. Pre-processing is a stage where you mesh the components. What is meshing? Meshing is nothing but dividing the 3D model into multiple minute small pieces. Why do you have to do it? For you to really understand where the change of behavior starts from. When it is a whole body, the change of behavior identification might be difficult. When you divide it into multiple minute small pieces, the change of behavior identification area could be easily captured. So it is very important that you do this pre-processing, and this pre-processing is called meshing. Today, globally, people would not believe that if there are 100 design engineer openings, there are 100 mesh engineers opening also available in the market globally, right? Because this is a very critical stage. The better you mesh, the better the output would be. What is better output? Closer to reality. As your output is closer to reality, then your meshing is strong. Then your simulation is strong, right? This is just for your understanding. And then you do the simulation, whatever you wanted to do. Once you've done the simulation, you go to the third stage to understand what a designer should modify to get this simulation to the requirement. Are we all making sense? So this is how simulation will also work, right? Do I have any questions until now? And this is the place where we get into the essence of the topic, right? Now, what is simulation aware design? We know what is design engineer. We have a little introduction about what simulation people do. And now we wanted to talk about what is simulation aware design. It is simulation aware design is like a design should not only look good, a design should perform well. What is performance? If I am talking about this mobile phone, it should When I keep it inside my pocket, it should not bend more than a particular millimeter. When I drop the phone, it should not break. So this is the performance. So when a design is right only when it performs under the load, whatever could be the load condition, right? So it is consciously modeling a geometry with multiple considerations. What could be that? Materials, their functionality, right? When you use right material and right features on your design, I'm talking about features now because we are going to talk about a lot of thicknesses, a lot of fillets moving forward, right? These are simple things which you can do on your design to improve the ease of the simulation and improve the accuracy of the simulation. See, on simulations, sir, the point is there is no wrong simulation, but can be a better simulation, right? Say, for example, okay, we will see more examples in this. So, what as a designer one should know is you should have these perspectives in mind when you already design. Instead of designing the complete component, sending it to a simulation engineer, and then he or she says, no, this is a wrong, this doesn't meet the load criteria, right? When they say like this doesn't meet the load criteria, then we will have to optimize the design. Instead of doing that, when you already have certain inputs in your mind and then design a component, you are a simulation aware designer, right? This reduces a lot of iterations, risks, and it fastens the product development. And this is what we talked before. Initially, we developed a product, then it came into computers. Now, a designer who knows all these things is also enabling reduction in the product development time. And that is what is very, very important. And this is introduction to simulation aware design. And how can one do this, right? When I say features, what can it do? What is it? Let us take a very basic bracket, sir, an L bracket. L bracket is very famous. Anybody can design an L bracket. But what people don't consider is it a strong component? Okay, I can definitely design this L bracket. It is just a small sketch, extrude. L bracket is done. And a small, I create this datum surface, I create a hole here. Bracket is done. But is it a strong bracket? Will it solve the conditions whatever I have? I kept a load condition of, say, for example, 110 Newton. At 110 Newton, it should not break. It can break. When should it break? Any load after 110, if it breaks, this is the right design. So now for me to understand the stress concentration, here it says it is more of red area. Why is it more of red area? This design is not the right design. Why is it is not a right design? Because it does not have the right radius what it should have. When the radiuses are right, when you have additional strength required features, see, this is the emboss what you can create, or this is a fillet, or this is a rib what you can create in between to increase the stress, to increase the performance by reducing the stress, right? Just the same L bracket with an improved radius and a rib in between enables a better results when it is basically an L bracket. Just to say, let us take a basic example. Sir, I have a notebook here. Okay, if this is the bracket, if this is how it is, when I try to add load on the other side, it is easy to it is easy to break. But if I have a feature here in between, when I add the load, it is not easy to bend, right? And that is what you should, as a designer, already consider when you design this bracket. Right? This is a basic example. The examples might get intensified as we go. Now we are talking about a lot of EV concepts. We are talking about batteries, etc., etc. So let us also talk about a battery tray simulation. If there's a possibility for any of you, if you go and see, you cannot see random ribs over a battery tray, because the position of this battery tray is very, very critical position. It might be experiencing certain loads from multiple directions. On this situation, if say, for example, if there is engine before this area, if there is engine here, there might be heat dissipation. Okay, on a battery vehicle, why should there be an engine? If there is some motors from the wheels, which is running, which is creating a heat, due to long time running, if this motor is generating some heat, there is going to be some heat which is getting transferred over this metal. How is this transfer going to happen? If there is no ribs at all, the transfer is going to be intense. Do you all agree? When you draw some ribs, these ribs are going to act as a place which will divert the forces or energy. When there is a load acting on this particular area, this rib will enable in such a way that it will divert the forces to multiple directions. Having said that, we will have to now divert these forces on the right directions. Now, having an unstructured rib structures like this or embossed structures like this, will it be better, or having an organized structure be better? I would not say the left thing is wrong, and I would not say the right thing is the only correct approach you can do. This will work on a different position on the vehicle. This will work on a different position. When here the idea is, we will all have to understand that these ribs are all designed considering the heat what you experience or load what you experience. It need not only be physical load, it can also be thermal load. Since this is EV battery, if it is some other component, it can only be physical load. Right now, the topic is, how am I going to design in such a way that the heat transfer is efficient and doesn't spoil the battery which is placed inside? So there is better or smaller stress concentration on the areas, not high concentration on the areas. Blue is generally, blue or green is actually good results. Red, yellow are all bad results. So that is the context, right? So what you will have to understand here is, with respect to the position of the component, these ribs play a critical role. When you produce, when you design these ribs, what plays an important role? From the previous chapter, from the previous topic, the radiuses, the slots plays a key role, right? Moving forward, how can this fillet influence? This is a very simple example, sir. A very small T bracket here. Without a radius, you see, there is no fillet at all. You see that the stress concentration is on the corners. When there is fillet, the stress concentration reduces. When there is a bigger fillet, there is no stress concentration at all. Right? Our intention is to, when you design a component, have these perspectives in mind. Right? So what is fillet? Fillet is enabling players to become very smoother, have better transitions. Right? Where can we find fillets? Generally on the corners of the part or over the embosses. We find this. What should be a critical input, or what is criteria for you to have a fillet? There are some thumb rules. So on which level will you have a green zone? On which level will you have a better zone, which is not right? There are some thumb rules, and these thumb rules are defined out of experience. When you are talking about internal radius, it is always better. This is the notes, sir. If you have some notepad or whatever, you can note down these points. It is always better for plastic components. Design guideline says that, this is out of experience we are talking about, right? For plastic components, internal radiuses can be 0.5 to 0.75 into the wall thickness. What is wall thickness? Thickness of the parent. When it is plastic, there can be multiple thicknesses, but there should be one wall thickness, class A thickness, right? That is wall thickness. So what could be internal radius? It should minimum be between 0.5 to 0.75 of the thickness. If the wall thickness is 1, the optimum thickness for a plastic material, which is 1 millimeter wall thickness, is 0.75. Value between 0.5 to 0.75. If you give a lesser value, then you will have this kind of stress results. Then your stress will be like this. If you have values between these things, when it is 0.5, maybe you will have this kind of result. When it is 0.75, you will have the better results. Right? How does this influence? This is not only for the simulation. What type of simulation will we do for this? I will try to understand if this is a producible part or not. For me to understand the producible part or not, I will study, if I'm going to produce this by injection molding, I will study how does the mold flow work like. So when I study the mold flow, I see like, okay, here the flow is not good. I will have some shrinkage of material there. Right? I will have some shrinkage of material. So what I can do, I use this proper radius, and this radius enables better flow in injection molding process. When there is better flow, you produce better components. There is no shrinkage of components, shrinkage of material at a particular area, right? So that is important. And similarly, what is understood is for sheet metal components, at least have 1.5 times into material thickness. If material thickness is 1 millimeters, your minimum radius, internal radius should at least be 1.5. Why? For the weld to penetrate better. And fatigue crack. When it is metal, when you apply a lot of load, there could be cracks happening on the corners. How do you avoid that? If I have this smooth radius or smooth radiuses on the fillets, I will have this particular aspect. So this is one particular aspect what a design engineer should have in mind, because you are doing all these things to enable good production, right? You're doing all these things not to support simulation person. Simulation person knows what to do or what not to do. You are doing all these things to bring out the part really well. This simulation person in between is studying if your part is coming out well or not. If you already have this thought process when you design the component, you become a better design engineer. And that is where you become a CAE-oriented design engineer, CFD-oriented design engineer, simulation-oriented design engineer. And that hybrid knowledge is the need of the hour. Are we all making sense? Right? And similarly, there are also other examples. Same, let us take the same L bracket, right? Even without adding ribs, only by increasing the radiuses, we will see that the force attacking on that particular area would be better. And again, when we are talking, see, you should not talk only about the internal radius. You are talking about the corner radiuses also. Here, if you see, the corners are also sharp. So the force tend to travel across. But when you have a nice shape over it, and that is why, okay, why this cannot, when you look at a particular bracket or when you look at some components in the car, you would see that why is it always in this complex shape? Why cannot it be very simple? Simpler design will have these kind of problems, because we are talking about producibility and longevity of a product. We talked about producibility. How do you produce? For you to properly produce, you will have to consider manufacturing processes. And after produce, how is the longevity of the product? When it has these kind of shapes, the loads will get divided properly with proper radiuses. We are only talking about a very basic concept, filletism. And this fillet plays a very, very critical role, sir. Right? And that is the importance of fillet. We could take it that way. So using proper fillet, if you know how to use a proper fillet, say for example, from this slide, if you now memorize at least 0.5 to 0.75 into wall thickness for plastic, 1.5 into material thickness for metals, if you memorize at least this and implement on your designs, you are already a hybrid engineer, CAE hybrid engineer, right? Because this is what is very, very, very critical when as a designer for a person to work on, right? But it could be the same material. A small change in the geometry would give us a fantastic result. Are we making sense? Right? If somebody can acknowledge, or Venkatesh, is there any questions? Do we have until now, or shall I continue?
Yeah, you have one question. Shall I read it out?
Please do.
What are the various new cutting edge tools model-based engineers should focus additional to MATLAB and Simulink?
Okay. We will cover this topic, sir. We will reach there. So during the process, we will reach there. So I will get there. Yeah.
No, Subbu, I request in your screen, there is a hide button.
Okay.
Once you press the slideshow, if you can hide the, yeah. Okay.
And I hope it is not a problem if I come out of presentation and look at the questions now and then, right? That will create a chaos. Yeah, I'll do that then. Yeah. So moving forward, now let us talk about thicknesses. We until now talked about what is the role of a fillet for you to be an efficient design engineer. Now let us talk about thicknesses, and we will also talk about thicknesses of plastic parts, thicknesses of metal parts, right? Why is it very, very important? Why using right thickness? We talked about wall thickness, right? Plastic generally has multiple thicknesses across the components, but we are talking about the wall thickness here. Why is it really important? This will increase. We already saw an example about mold flow. When the radius is less, we also talked about shrinkage or warping. What is warping? Warping is reduction of thickness at a particular area. Shrinkage is crowding of thickness, crowding of material at a particular area. Right? Structural stiffness. What is structural stiffness? The previous is a right example. Right? So this is it. A thickness also plays a critical role on these kind of aspects. So we are again talking about how are we going to give out an efficient product, not a beautiful product. A product is good when it is not only beautiful, but it is good only when it is functioning properly, right? So how can these things happen? One should maintain uniform wall thickness. On this wall thickness, there could be a place where there is a need of changing thickness. Since it is plastic, since it is mold, it is very easy for us to design having multiple wall thicknesses or various wall thicknesses. But advice is to not use those things, because it would tempt us as a design engineer, it would tempt us to increase the wall thickness on a particular area to avoid certain features like ribs or embosses or whatever. But it is always advised to have uniform wall thickness. If at all there is some changes you wanted to do, let it be plus or minus 10%, because that plus or minus 10% would be taken over by the tolerance values, would be taken care by the tolerance things only. Right? And when you do this, it will reduce the warpage because material flow will be very nice. And similarly, one should also think that you should not make a part more thicker. There is always a thought process for us. I had the same thought process when I was a fresher, when I was 1-2 years old. Okay, now I want to build a strong product. Let me increase the thickness. Increasing thickness is not going to increase the strength of the part. That will only increase the weight of the part and not strength of the part. Strength is different, weight is different. That understanding one should get. So let us not make a thicker part. Instead, we will have uniform wall thickness and increase the strength by adding ribs, right? And adding gussets to improve the structural rigidity. Because when it is over thickened, you also get sink marks. What is sink marks? When you talk about, for you to know sink mark, one should know at least injection molding process and introduction of injection molding. It is getting molded from multiple. The raw material is getting injected from multiple areas. Whenever it gets injected, there is a place at which it sets up, and these injector pins should go out. And these injector pins, when it goes out, there it leaves a mark. That could be one mark. And it is not about only flowing; it is also about the pressure or force at which the part would be formed. And that pressure, when it is more, you would also see some sink marks on it. So these are all the probable problems what one would face if the thickness is more. So let us all have in mind that having a thicker component is not making stronger component. You can make stronger component with thinner thickness also by adding some ribs and gussets. So, and again, in these thicknesses, whatever could be the thickness of the part, on the corners, on the draft areas, if you have the right draft angles, right fillet integrations, that would add a very good complement to the component. This would reduce stress, or this would avoid stress getting increased, right? And this is just an example. This is just an information for you, sir. You need not even know that, but as a story, you can have this in mind. Meshing has multiple quality of meshing, right? This mesh should also be smooth. Say, if you look at snake skin, the structure of the snake's skin is uniform throughout, and that is how a mesh should look like. It should be uniform throughout. It should flow seamlessly. If there is a smaller radius, this mesh will not flow seamlessly. There would be some disturbance or distortion at a particular area. And this, when the mesh situation is bad, it would not give the correct simulation result. I also mentioned that there is no right or wrong result, but when I'm saying now that not right simulation result, this means that this result is not closer to reality. So a mesh should be very smooth or very clean. So the simulation results are closer to reality. These days, there are multiple technologies for us to do this auto mesh, etc., and do multiple aspects of it. But we should also have these drafts, fillets, radiuses, thicknesses in mind to enable proper meshing only at first stage. When proper meshing happens, the simulation results will be closer to reality. When I say closer to reality, this doesn't mean that all simulation results are away from reality. We are talking about plus or minus 5% probability tolerance, right? So that also is there. So having a proper draft will also help in proper ejection. What is draft angle now? We have a okay. Let us take an example. We have a product like this, right? This is how the injection goes, and then it comes out. If, say, for example, the product is something like this, the tool will go in, but it will not come out properly because it is not proper draft angle. When the draft angle is proper, when it is properly open, now this becomes a proper draft angle. When it is properly open, the tool can go in and come out. When it is closer and closer and closer and closer, the tool will go in, but it will find difficult to come out. When it finds difficult to come out, what does it mean? You are reducing the life of the tool. So now, as a design engineer, you are also thinking from a tool's perspective. So you work as a tooling engineer also here. So you provide proper draft angle for what? To improve the tool's life. Because you pay, say, for example, I pay 1,000 rupees to produce a tool which can produce 100 pieces, right? If I produce only 80 pieces, I am wasting 20 pieces. 1,000 rupees is not worth it. So what is important? If I pay 1,000 rupees and if the tool is capable of producing 100 parts, I should take out 100 parts out of the tool. If I don't take out those 100 parts, I am wasting the tool. How can I make sure that this tool can produce this 1,000 parts? By adding these kind of things in the design. And this will enable smooth simulation process also. So everybody is finally working on bringing out nice product. Right? This validation person, the time or energy or money what we spend here, if you have this particular skills, this time, money, and energy would reduce a lot, and which is what is industry wanting today. Right? Moving forward, this is okay. For example, this is a plastic gear housing. Okay, how will the load act or stress behave when you have multiple thicknesses? How will the mold flow be when the part is such a complex part? Right? Now, the left side part can look like a simple part, but what is the problem here? The thicknesses are varying. The sharp, it has sharp wall corners. So the flow would be very, very less. What is here? Here we have uniform thickness, and the remaining strength we are gaining by these ribs and fillets. So the mold flow is also nice. So I am working properly for the tool. And this is the type of result what a simulation engineer will say. So you would have initially produced this part and sent it to a simulation engineer. He said, no, this is not working out. And then you improve, and finally you get a product like this. How will you get a product like this? After understanding how simulation works, what does this guy say? I mean, how does this part behave, etc., and then you add ribs, features for increasing strength, for increasing mold flowability, for increasing the production possibility. You increase radius, and then you do all these things. When you reach here, everything will be green. So you can still produce continue production of the part. But if you already know these kind of constraints, and you can reduce a lot of iterations in between. That is the thought process. Right? This is how a design engineer should think. This is an example for a plastic gear. Similarly, let us go to sheet metal now. Sheet metal, what does thickness play a role? How does thickness play a role on a sheet metal component? Right? Let us consider BAW parts. I am a fan of BAW parts. So let us consider BW parts. Casting and forging could be at least little related to plastic molding processes. Thickness plays, we will follow the same pattern. Why does thickness play a critical role in sheet metal? Because it is very, very important for crashworthiness. NVH, type of the shapes, and the vehicle weight. Okay, these 4 words, as a word, it looks very, very simple. But how does it reflect? Like I very initially told, a design engineer should design considering manufacturability, assembly, and very importantly, functionality. So functionality, it is very easy. When we talk about door, it is very easy. What is the functionality of a door? People would easily say opening and closing. The opening angle would be more. Window should go up and down. But people sometimes tend to forget the side impacts effect. Similarly, on the hood, people talk about open and close, aerodynamic structure, etc., etc. But people tend to forget the frontal crash, or don't know how to implement the frontal crashes influence on it. Today, after the session, if you can go and open a car's bonnet, a car's hood, you would see a lot of structures on the inner panel. Most probably Y or an emboss or a honeycomb structure. The reason for those structure is this crashworthiness. Meaning, when there is a load acting during a crash, this structures inside will divert, delay the energy which is created during the process. These embosses will also absorb certain portion of energy. So what does these embosses or structure do? They absorb energy, divert energy, and delay energy. Where is it trying to divert? Drying outside the car. Why is it delaying? When it delays the process, the intensity reduces. When somebody slaps me, it will pain very high in the first 1 minute. The last 5th minute, the pain reduces. That is the same principle. Right? So when we talk about crashworthiness, we are talking about functionality of a component. So understanding the functionality, how does thickness play a critical role on this functionality? If I have a more thicker part, it will not break. If it doesn't break, the load is still traveling. If it breaks, the load is used. Correct or not? Hoods are today designed to break. You are designing a component to break during a collision, because if it doesn't break, the load will travel across the vehicle and it will create a huge impact inside the passenger cabin. So thickness plays a critical role there. Right? And again, noise, vibration, and harshness. Similarly, the shape, how does it look? Those are the embosses, whatever we talked about. And more thicker the component, you increase the weight. When you increase the weight, you decrease the performance of the vehicle. And that is why thickness also plays a critical role in sheet metal design. What can one do to consider efficient design? See, plastics are single components. Sheet metal components are generally assembly pieces. Mostly we'll assemble these components, correct? So let us take A pillar assembly or B pillar assembly. The outermost part of the A pillar, outer or A pillar inner, is not going to be more than 1 or 1.5 millimeters. And on some particular area, we will have to add some reinforcements. What are reinforcements? Why are reinforcements? Reinforcements is additional material added on a particular area locally due to the, why are they added locally? Because there is a loss of that energy on that particular area. Why is there a loss? Due to its surround components. Let us take an example. Hood only we'll take it. Hood, when you open, you have these hinges, right? On the inner panel, on the left side and the right side, there is going to be hinge reinforcement, LH and RH. Why on the left and right above the hinges we keep? Because hood inner panel is only 0.75 millimeters. When you add a hinge, which is a heavier component, over a 0.75 millimeter sheet part, it will tear. It cannot take the load. To compromise that loss of energy, we add a component called reinforcement, which is 2 to 3 millimeters. Right? So, using proper thickness for the reinforcement is a very critical important. And again, like plastics, we also see we will have to slowly bring down the transition. From here, let us not change a very big dimensions of the shape. We shall have to slowly bring the shape. And that is this proper flow also. This flow is for the load, not for the material of the part. Even this material could be produced on the sheet metal. Anyways, you are only deep drying it. But how will it impact the performance of the vehicle? That differs. Right? And similarly, when you do these thickness changes, we will have to do gradually. From 2 millimeters going to 0.7 millimeters is a bad mistake. So what you can do? You can do 2 to 1.5. 2 to 1.5, 1.5. This could be a gradual decrease on the thickness change. Right? There can also be some shell elements used, 2D shell elements or 3D shell elements. We can talk about maintaining continuous shell connectivity across the wells. Right? So, and also when you're doing a particular assembly on the weld, that particular assembly should throughout have uniform thickness. When you have multiple thicknesses across multiple welding points, the strength of that assembly would be lesser. Right? Same way like how you simulate a plastic part, you simulation people will also simulate a sheet metal component. They will see the peel out test. They will see the strength of the assembly. When these things are all not followed, the test will fail. Example. Right? This is a side impact zone. It is very common to have multiple easier sudden jump from 2 millimeters to 0.7 millimeters of reduction. Could be a stronger material and slowly it reduces. But the crash output would be very, very hard during the spot weld area. But when you are slowly reducing the thickness from 2 to 1.5 to 1.5 to 1, then you will have better performance. Right? Moving forward. Now we will have to talk about the load integrity. Load integrity is how does this load path play a vital role? So how can your design influence on this load path? Whenever there is a collision, this is how the load transfer. The load, 95% of the load initially travels via the engine column, and then out of which it goes via the floor. Right? A major portion then gets diverted to the upside of the car, which is on the A-pillar roof area and on the floor area. And that is why during a collision, people tend to jump because of the load. Right? Even though you go on a flat road, you would have not even be on a bumpy road. When you hit, you jump because of the load and the force also. And also the vehicle wobbles. Similarly, you will have multiple loads from multiple directions coming in. How can you have proper load path? What are good things one should do to ensure proper load path? So during this collision, the load goes outside the car and not inside the passenger cabin. Intention here is the load getting inside passenger cabin should be very, very less when compared to the load going outside the passenger cabin. Right? That should be the thought process. So during this motion, it should either go out or on the sideways. So how will I create my embosses, or how will I do these things? Do all these load information efficiently during a design process. How will this impact the performance of the vehicle? Because ultimately we are talking about performance of the vehicle. For this, there are certain aspects which one should follow, and that also is again basic blended transitions and properly using radiuses and fillets. It would be surprising for a person to know, for a design engineer to know, if you know to use proper radiuses, proper thicknesses, proper fillets, your design would pass in even second iteration or first or second iteration. First iteration would definitely not pass because requirement would change. Second iteration. Then you become a very efficient design engineer. When I say don't overcomplicate the geometry, it means you should not have complex structure wherever it is exposed to, wherever your components are exposed to. There should not be very critical structures on the places wherever you are designed to. Why? That would cause a lot of meshing problems, which would lead to wrong results, results not relative to the reality. A smoother and a normal design would be very helpful to reduce the stress on the particular area during the crash simulations. Right? Similarly, what could be the best practice? Whichever is the load carrying area, keep that part very simple and clean. What is very simple and clean? Not critical structures or not critical shapes on it. Right? Whenever you're talking about on these particular areas, don't even think of having aesthetic items. So generally, when you see in the vehicles, it is very easy to mention Suzuki in the center, right? But they always mention on the corners. It is very easy to mention Safari on the center, but they used to mention on the sides of the car only, the name of the car. But today we are seeing that Nexon is branded in the center of the panel. How is that achievable? The position is way above than a rear impact, and the back door is way inclined. So the first point of contact would be the bumper, and the bumper reinforcement will take a lot of load. Right? So these are all the considerations one should have. What can you do? You should have blended transitions, smoother measure flow. When you have smooth transition, your mesh flow would be smooth, so your answer would be safe. Again, have fillets more than 2 millimeters around junctions. Right? Chamfers on the corners are called stress ghosts. This is just a word which I wanted to tell. If you have sharp corners, chamfered corners, you are talking about carrying a lot of stress already. So always have curved or conic transition. So it enables proper, it removes the stress. It releases the stress from the particular area. Right? Similarly, one should also have proper connectivity from one part to another part. When I say connectivity, we are not talking only about spot welding here, nuts or weld. I'm talking about the individual part. Right? So if there are small, if there are very minor gaps between the surfaces, or if it is a small part which got to be attached to a bigger component, always try thinking or try seeking in such a way that you join these two pieces together. Then welding or nut bolting or using screws, bolts, etc. Right? One should also have multiple. It is very nicer for you to use this Boolean operations like merge or join. I have prepared this particular surface. I had prepared this particular surface. When I join, you already give only radius, and it becomes single phase. During the design process, from the production process, we are talking about failures, node stiffness zones. From the design process, how can I use this Boolean methodology to achieve that particular activity? Right? One can have multi-body contact regions instead of one particular area, and that is why if you see across the vehicle, you see multiple points having spot welds. It is sufficient even if you have one or two reduced rate, but they don't want to reduce those spot welds because they are ensuring the performance of the vehicle. Right? So that is what is important. And again, what is very important is one should avoid load carrying geometry. What can be a load carrying geometry? Right? When there is these kind of sharp corners, right, is a load carrying geometry. These kind of smaller radiuses is a load carrying geometry. Right? One should not design to increase stress on a particular area. If you adding ribs also is very nice, but if you add the rib on the corner of the component, if you add the rib in the corner of the path, that will create a different type of load structure. But if this rib is towards the center of the component, it enables proper strength. Right? So these ribs should be positioned in such a way that they intersect properly and they merge to the load bearing surfaces properly. Right? So what are these load bearing features? These load bearing features are again like I previously mentioned. We are not, if it is thick, it doesn't mean that it is strong part. Right? The load generally follows the geometry only and not the thickness. So if you're adding some material to a particular area, the load is getting distributed. The load is getting distracted there, right? So and if that material is on the place where the force should not flow or doesn't flow at all, then it is only a bulk. It is not something which is doing performance, something which is performing inside the vehicle, right? So, and that is where you use these kind of arcs or corrugations, right? Basic example like what I have mentioned here is a thick wall near a bolt hole would not reduce the bolt pull out stress unless and until you have the surrounding ribs, because these are the ribs which is carrying the tension instead of just having a bolt holes, right? So, and that is why this load path is a very, very critical information. And if you see the differences here, there are multiple shapes, which is not at all needed, which is not at all the intent. And this is only creating stress here. Here, the thickness is very much varying. The ribs are all not flowing together. And now, when you make optimum changes, you also see a very smooth flow of transition, right? Not ribs not fully getting connected are all a bigger problem, which one should not at all afford to make that. And see, and this area is totally avoided. And this is what one should think about. Of course, here you are talking about material addition, or you can also think about material deletion if I have completed here. And this depends upon the performance of it. So as a summary, and that is why I had this statement across all the slides about this load topic. The structure is only as good as its weakest link, and the load path integrity ensures that no link is left behind. So what is load path integrity? You should not have any link left behind. That should be your thought process from the beginning when you are designing a component. This is a left behind design. This is a non-left behind design. Right? There should not be an extra protrusion kind of thing over a design. Right? This is the thought process. And let us talk about battery tray. Initially, I was also talking about this example even before the topic started. It is also easy for you to not at all have any rib and just have a tray over which you can place the battery. But the load impact would be more because of the intensity it carries. When you have these kind of structure, the load is getting differentiated or distributed accordingly. Because that the weight of the battery would cause sagging to the tray, and then it doesn't function properly like how it should function. By only adding these kind of structures or ribs, you are reducing this deflection by almost 80%. Right? And before getting into this common modeling, I'll just see if there are any questions for me. No questions. The minimum bend radius for sheet metal is 1T, right? I saw 1.5 T. Okay, 1.5 T is optimum value. 1 T is the minimum. So we thought about, okay, red, blue, green. 1 T is where blue starts and 1.5 T is where it goes to green. 1 T is not a mistake, but 0.5 T is a mistake. 0.8 T, 0.9 T is a mistake. Stress risers are, okay, if you're, okay, let us consider T bracket. If this area doesn't have radius at all or has very small radius, that area is a stress riser. Where is new cutting edge tool model based engineer should focus? Additional to, okay. Yeah, we will see that, sir. Yeah. I have a different perspective over tools altogether. Okay, any which ways I'll address that and then go back. Today, MATLAB is nice thing. OpenFOAM is an emerging market. Python, of course, you will have to know to do any of these things. Apart from these things, I have one particular perspective across when we talk about designing tools. Designing tools are simulation tools also, like HyperMesh or ANSYS, those kind of tools when we talk about. I have a kind of a perception, sir. Am I taking a lot of time? No, yeah. I'm having a type of a perception. See, it is not important that you know multiple tools, but it is very important that you know one tool properly. One tool really well. What is properly? What is really well here? Let us take an example. If I got to make this tray only in CATIA, since we are talking about tool, what will I do? Datum plane, sketch, extrude, get this component. NX, datum plane, sketch, extrude, features. Creo, datum plane, sketch, NX. So whatever you are going to do, the process, the generic approach is going to be same only. Only the tool interface is different. So it is not important to know multiple tools, but what is important is it is important that you understand the engineering behind the component. You understand, you should have this generic approach. What steps should I follow to do this efficiently? That is what is very, very important. Right? Now, continuing the presentation, what could be common mistakes a design engineer generally makes? This could be, we are actually nearing the end of the presentation, I would say. What could be common mistakes? I also have some examples here, which one should not do, right? A geometry should not have any breaks or discontinuities. It should be continuous and it should have this flow. Whenever there is a flow, this transition should be gradual. It should not have abrupt thicknesses, or it should not have sudden changes in the roads. Right? When you are trying to use reinforcements, when you are trying to use reinforcement, those reinforcements should have ribs or bosses. So the load change direction is proper. If you don't use this, the load force exit regions will be open, which is not the ideal. Right? Meshing, on the meshing aspect, one should have clean load path with fully well-shaped elements. One should not have sharp corners. That is the thought process here. Or thin webs, which will lead to poor meshing. Right? So you are doing something which is supporting the machine engineers. You are doing something where the intensity is reducing. Connections, try to merge as much as possible. Or tie contact zones correctly. What you don't have to do is don't rely on constraints to force the load gaps. Don't force in the load across the gap. These are common mistakes one should do, one should not do, or optimum things one should do, right? And we see a lot of type of problems. And this is the image which talks about what is right, what is not right. What could be better, what could have been avoided. What could be, so we talked a lot about warping. What is warping? Material getting accumulated. How can gussets minimizes the warping? So when I add these things, these kind of warpings will be avoided. And similarly, this is a poor design. This is a good design. This also is a good design. Right? And similarly, we have when you have sink marks, how does it work? When you have no sink mark, what is good for you? Without sink mark is what is good for us, right? And how can the connections work on? How do you avoid these kind of sink marks? What is uniform? What is not uniform? Right? So don't use small holes, or on the critical load bearing area. Don't use your aesthetic things, right? And similarly, when you are having multiple panels aligned during this welding process, it is always better to have a relax to it and then keep these panels so the load force is same. The load goes on the same direction. You don't divert, or it enables faster movement outside, right? So you will avoid these unintended gaps or without any proper these things. So one should not break the continuity of the force. Now one should cause one should not cause this floating cells or stiffness on different areas, stress loads on different areas, right? When you don't choose right thickness of the material, you may experience these kind of aspects. And also don't jump from bigger thickness to smaller thickness drastically, move gradually, right? These are the key points which I've been telling throughout the presentation, because this is very, very important for you to expose yourself or exhibit yourself as a simulation engineer, right? So what are the problems? So unnecessary spots are removed, overlapping panels are taken out, abrupt thickness changes are omitted, right? There are you have clean flanges. Because part of these are, this is a 3D. What is it? This is scanned component, so it looks a little messy. But this is how after the part is produced, this is how it looks like, right? But these are the gradual tapers is the key point you should take. Spot weld marks is the key point you should take, right? So instead of having different panels, you make it as one merged panel, right? So what other problems an engineer could make is again reducing the number of welds or number of joining elements. Don't do that. If it demands 10 spot welds, go for 10 spot welds. And between one spot weld to another spot weld, minimum is 12-13 millimeters. Okay, 10 millimeters. The reason is that spot gun diameter is 10 millimeters. You should have that flatness on that particular area for this gun dia to go and get placed. If you don't have that flatness, you will not have effective welding. Not effective welding is not effective functionality. Ultimately, it goes back to the functionality again. Right? And similarly, non-manifold geometry or overlapping bases. What could be a probable mistake? What we generally do, the flanges or the corners have duplicate faces. Edges will not have missed. You should not have flat edges, corners, sharp corners. You should have curved corners. There should be some logical angles. Why is this 7 degrees? Why is this 4 degrees? Right? So these are all the aspects one should have in mind. And this is just an example of how strength plays a role, stress plays a role, or whatever. The left side is a phone case, phone without a case. How will the stress travel? With the case, how is the stress traveling across? This is a simple design. I chose phone because it is a simple design, right? It is just a basic cuboid with a basic thickness, but it has multiple designs in it. When the corner without the case, the corner is going to be a little more sharper, so the impact is more. With the case, the corner is a little more wider, so the impact is lesser. That is my thought process, and that is when you all these time I was talking about radius, corners. This example will solve that point. This example means that radius is smaller, impact is more. Radius is bigger, impact is lesser. Are you making sense, sir? Right? Before going to the next stage, do I have some questions? No. Yeah. So the projection, what I would at least see is as for you to be this CAD CAE hybrid engineer, skilled on both CAD and validation, you can take this in phases. I am not telling that you should know all these things right now for you to flourish. No, we can take this in multiple phases. What to learn, how to learn, and what could be the activities. So on the phase one, when you are in the initial stages of career, engineering fundamentals is very, very needed. Strength of materials and mechanics is very, very needed. Drafting GD&T. Similarly, these are the tools. It is beneficial for you if you practice. Right? Basic mechanical components, 2D to 3D. Yeah. Or take part in design challenges. On phase two, you should do some specialization. Specialization on the CAD, on the CAE, and combined together. On the CAD, you should know start all these smaller components. You should know how to assemble them, how to surface them. You should know how to staller and stack up them. Understand the design intent. That intent is this functionality, manufacturability, and assembly of it. DFM is designed for manufacturing. DFM is designed for assembly guidelines. knowing these things, you should have developed when you are at least 3 to 4 years experience. On FEA, you should at least know meshing boundary conditions. When somebody shows you the result, you should know, you should be in a position to understand the result. Right? Model, thermal or fatigue analysis, material properties and load parts. Combined, perform static structural analysis. So you had designed a component, you understand these things, perform a static analysis for it. You have this tack-up analysis, simulate a complete assembly and understand how does it work. It can either be in ANSYS or any other tool. Validate design changes via the CAE program. Another phase is after by industry readiness. This is where you become ready. If you have 4+ years of experience, it is needed that you have the skill. Design for simulation, which is load parts, fillets. FEA result interpretation and optimization, you should must have. You should communicate this CAD and CAE iterations correctly. Example, suspension arm or whatever. Improve the plastic housing for stress or warpage. These are basic examples. Forget about the examples, sir. These are the must-have abilities what the industry is expecting today. Right? Having the right skills, you can expect these kind of careers. You can expect these kind of career roles. Right? And you can this is just a tip from my side, like at least working on 5 end-to-end design validation. What is end-to-end? You should design, you should also validate. When you validate, you will have some problem, you should redesign. Contribute to some open sources or university competitions like Baha, FSAE, right? Get certified on certain tools. Python or MATLAB, very, very important for parametric optimization. Right? So this is where I would want to stop. And now I am very open for the question and answers.
Thank you, Mr. Subbu. Folks, please, I am activating the mic. Please feel free to ask any questions with Mr. Subbu, or if you choose to post it on the chat window, that is also fine.
Okay, we are also quite a number.
You should be able to unmute yourselves. If there are any questions, Mr. Subbu can take up question.
Yeah, since many people are here, if you doesn't strike anything right now, if you have some questions, you can also fill in this link. This is not the same link like what Venkatesh had sent. This is my own. If we cannot address your query live now, we will reach out to you separately, and if you can also reach us out and ask your questions. We'll try to answer them. But you can at least react if if the session was interesting or not, or if it was boring, if it was more content or too much to digest. If you can give at least that level of feedback or impressions, like at least thumbs up or thumbs down, would be interesting for me to know. Thank you. Say thank you. Can we have a better timing? Venkatesh, this information is for you.
Yeah, noted, Mr. Mohammed. Please do fill it up in the form itself. We'll in the feedback form itself. We'll collate this as well. So for working professionals, like usually we have been doing these sessions at Friday 3 p.m. only. But definitely we'll take your. We'll make sure to share the recording with you.
Hello, sir.
Yes, sir. Ankit Jaiswal. Was it
Yeah,
clear?
so like what are the like stress risers? Like you mentioned that stress risers. Like can you like please explain in like some detail stress risers?
Stress, stress risers are nothing but, okay, that is not an individual feature. That is not an individual feature which gets into it. A normal rib can also become a stress riser. Or if you don't have any radius also, that also is a stress rising criteria. It is a criteria, right? So avoid using these type of points is the context. Say, for example, if it is just a minute. 1 minute. I'll just share the screen and try drawing on the same presentation if possible. Yes. This is the bracket, right? I don't use any radius at all. This is a stress rising criteria. If I have this rib here, and if this rib thickness, if the rib is not positioned properly, if it is too much over the corner of the component, then that becomes a stress riser, right? So these are all the things what one should avoid, and that is what is stress riser. Anything which is contributing to increasing the stress or load at a particular point is called a stress riser. Are you making sense? Thank you.
There is a feedback from Mr. Amit on having some in-depth analysis on engine casting.
Okay. Will be helpful if there was some in-depth analysis on engine casting, structural part analysis like crankcase, block city. Yeah. Absolutely. That it would be better if an analysis person comes and takes this. The context of this session itself is how important is knowing CAE for a design engineer. So this session is not to teach simulation, but it is also important that the in-depth analysis of engine casting, structural parts analysis, those kind of things, to know how to analyze is also very, very important. I agree to it, but that should be from an analysis expert, a person. I mean, maybe I can bring my ex-colleague also to do this. Point is taken, Amit. But the idea of this particular session is to tell design engineers how important it is for you to know CAE principles and what kind of impact that could create when you implement those principles on a design. Many people have the same feedback. Gunashekar and Mukali, Shruti. Yeah, many have said okay. Yeah.
Folks, we can have another 5 minutes if there are any more questions. And I have also shared the feedback form and the chat window. Kindly take a minute to fill it up. Any suggestions or any issues with the time slots or anything, please make sure to fill it up. We'll also share the recording of the session if you request there.
CAE and CFD, where these exactly used for what type of component? Okay. Difference between CAE and CFD. Okay, I started the conversation like this. Any simulation on the component can be called a CAE simulation. Any simulation around the component we can call a CFD simulation. This is a basic perspective or an overview of how to differentiate CAE and CFD. Any simulation can have both. I mean, CFD simulations is generally thermal analysis and fluid analysis. Okay, if your component is going to be exposed to a fluidic behavior or a thermal exposure, then you do CFD analysis. Else you don't have to do a CFD analysis. I don't have to do CFD analysis for marker. For a marker, I don't have to do a CFD analysis for a marker. Instead, but it is very needed for me to do CAE analysis for a marker to understand how much load does it. Can I keep it like this? Can I force it like this? What force does it take? Right. So, what simulation is for what component is a wrong question. Simulation is done for a purpose, to understand a purpose. If I wanted to understand the thermal behavior or a fluidic behavior of a component, I try to do CFD simulations to understand it. If I wanted to know the strength of it, strength of a component, the load bearing capacity of the component, then I do a CAE simulation. So that is the difference between basically CAE and CFD. So on the whole, what we can say is, if you do a simulation on the component, I'm bending this. Bending simulation is a CAE simulation. If I do something around the component, consider this as a car around a component, I do aerodynamic simulation. That is a CFD simulation. This is it. As a stamping feasibility simulator for the critical aesthetic parts, how it will make easier before simulation. Stamping feasibility simulator. Example, two-wheeler exhaust silencer assembly. Yes. Stamping is for the critical aesthetic parts, how it will make easier before simulation. I don't understand. Are you a feasibility simulator? Are you a stamping feasibility simulator, or are you asking if I am a stamping feasibility simulator? I wanted to understand critical aesthetic parts. How does it behave? How will it make easier before simulation? Well, critical aesthetic components. Okay, I don't understand the question completely. Yes, you are a simulator. Example, two-wheeler. Oh, okay. This is the continuation. Okay. How it will. Okay. Yeah. Now, okay. Now I should read this first and then example, two-wheeler exhaust silencer assembly. Okay. So, how is it critical, or what should be made? So here, when you specifically, I'm talking about exhaust silencer assembly. No, okay. Exhaust silencer assembly is an aesthetic component, agreed, but it is a performance component. So it can, when it comes to performance, materials play a critical role. So what material are we adding there is also a very important aspect. I cannot add aluminum there. My catalytic converter should be on a particular material only. So for before simulation or after simulation, whatever it is, from the functional perspective, material plays a key role when we are talking about exhaust silencer. Since this is also an aesthetic component, I would not 100% agree that it's an aesthetic component. Today we are talking about multiple types of exhaust assembly, so it can be considered as aesthetics for two-wheelers. I agree, but it is a performance component. If this silencer has a hole, gets a hole because of this severe road conditions, that would be the simulation criteria for this particular component. That would be a CAE simulation. So they do this chipping, stone chipping simulation, and understand at what intent that this silencer breaks, and what load or what force does it breaks, and on what light does it break, and it creates a different noise. Yes, TVS STMNL, KTMNL has only at the bottom of the wheel. So here it is all about the performance of the silencer. So performance means it is all about right material and right thickness again. Right? How do we use this properly? Should be the context. Yeah. See, when the silencer is not only about the exhaust, it is also about when it doesn't work functionally, it creates a lot of environmental damage. It creates a lot of noise pollution. NVH damage is more. So that is why one particular example would be this chipping, stone chipping simulation would be done at a particular speed on a particular road condition. That would be simulated and understood when it breaks it. And then proper countermeasure is taken to also keep the aesthetics and also make. Now the materials, there are more competitive materials available. Initially it was only strong iron which was used or basic materials. Now there are more malleable and at the same time stronger materials also available in the market. So it is all possible. It is not about easy or difficulty. It is the same only. Any institution in Bangalore? Institution? Yes, we have an office at Bangalore. Used for what type of compound? Yes, there is bigger difference between 10 millimeter, 12 millimeter, I mean higher thickened component on the CAE perspective than the thinner sheet metal components. That is definitely there because it is all about the performance only. No, see the process what you do on CAE would be similar, but the outputs is completely different. The expectation itself is different. Where will you need a 10 millimeter, 20 millimeter component, right? You will anyway, when you do a bending simulation for 2 millimeter component, the simulation process is same for 2 millimeter and also for 10 millimeter also. But see, okay, this is how I would want to conclude, sir. In simulation, I initially told that there is no wrong result. Why did I say this? Because they are set a requirement. You are being set with a requirement. Okay, I am preparing this. I am preparing this remote. This remote should work up to particular load. I am setting this as a designer, as a project leader. I am setting it should work until 20 kilonewtons load or 30 kilonewton load is the requirement set. Simulation person studies if the component works up to 20 kilometer load. So he or she simulates a 20 kilometer load and says how does the part behave at 20 kilometer. If that is okay or not. So that is why simulation there is no right or wrong result. They are studying what you have given as a designer, right? So if it is 40 newtons, it will break. So the same component, when 40 Newton load is applied, the result is going to be different. 20 Newton load is applied, the result is going to be different. But the process is same. The load is different. So the load is what the requirement comes from it. The project requirement says this is the load which my product should meet, right? So you cannot say that this simulation is wrong. This simulation is wrong. The approach on a simulation might be wrong, and that is what is very, very important. And that simulation engineers will take care, right? With respect to the thickness change, simulation process might not change. Results will change. That is my point. Yeah. And with this, I think we've had Khalil Basha. You'll Venkatesh, please help Khalil Basha. He wants to know where our company's address is. Yeah. If there is any more questions, we'll take. Else, please check the sheet, whatever was uploaded before, and do contact us. Thanks for your time. Means a lot. Spending time on a Friday evening during office hours is nice. Shows your interest. Thank you, Venkatesh, for also organizing this. Hope to see you all soon on the next session.
Thank you, Mr. Subbu. Thanks everyone for joining in. Any other questions, like Mr. Subbu said, please fill it in the feedback form. We will take it off the session. Thanks once again for joining in.